Hi, welcome to part 2, day 2 of related rates. Now we're going to take a look at one of my favorite questions here. It's called the shadow problem. Now the shadow problem does involve similar triangles again. So the very first question we're told is Gandalf stands 6 feet tall and can walk at a rate of 5 feet per second towards the light pole 16 feet tall. Now the first question is saying at what rate is the tip of a shadow moving when he is 10 feet from the base of the lamp. So I'm going to draw a picture here. So I'm going to draw a lamp first. So here's my lamp. We're told that the lamp has a height of 16 feet. Gandalf has a height of 6 feet. So I'm going to draw Gandalf here. Now what happens when the light comes down, it's going to hit Gandalf in the head and go straight to the ground. And we have this length right here. And there's the shadow. That's length of Gandalf's shadow right there. Now the question says, at what rate is the tip of his shadow moving when he is 10 feet from the base of the lamp? Now remember what I told you earlier. The biggest hint I can give you, if it changes, it gets a variable. So what I'm going to do is, I'm going to go through this picture and find out what's changing. Now, as Gandalf heads towards the lamp, remember he's heading towards the lamp, right? At 5 feet per second. Will the distance between Gandalf and the lamp change? Yes. So I'm going to call that x. Now, it talks about the tip of the shadow. Well, the tip of the shadow is really the length from the pole to the shadow. There's the tip. Okay? Will this distance, total distance, change? Yes. So I'm going to call that y. Okay? Now, there's one more part that will change. What about the shadow itself? Absolutely, that shadow will change length. As you walk towards the lamp, the shadow should get a little bit smaller. So, what can we call this? Yeah, we can go ahead and call this L. Now, we can call it L, or what we can say is what L really is. It's just the length of the shadow, the tip of the shadow, minus how far away Gandalf is from the pole itself. So we can say this is really just y minus x if we want. Now, will the height of the lamppost change? Nope, so we keep that 16. Hopefully Gandalf won't change height. He'll still stay 6 feet. So there's my picture here. So what I'm going to do now is write down everything they tell me. He's walking at a rate 5 feet per second towards the lamppost. So that's telling me, that's dx dt. That's this change right here. He's walking towards. This distance is decreasing. Now, it's going to be negative again, like we talked earlier, because he's walking towards. And when he's walking towards, that means that distance is getting shorter. So we say if you're walking towards, it's negative. Away from your velocity, it's positive. Okay? That distance, the distance is getting smaller. So we say it's negative. It's a negative velocity. Now, did they give us anything else? Yes, they tell us x is 10 feet. X is 10 feet. Now, I'm not going to plug the 10 in here because remember, that's going to keep that as a variable. I'm going to put in the equation if I need to. So now I need to come up with an equation, and this is very easy. This is just, from geometry, a similar triangle. I have a big triangle, and I have a little triangle. So I'm going to use similar triangles. And to do that, very simple to do, I'm going to look at the big triangle versus this little triangle. Well, for the big triangle, the 16 matches up with the length of the y, which, by the way, is what we're trying to find here. We're trying to find how fast this tip is growing, so we're really looking for dy dt in this case. We're looking to actually find dy dt here. So that 16 matches up with the y. Well, I'm going to look at the corresponding parts for the smaller triangle. The 6 goes to the L, the length of the shadow. But I don't want to call it L because I don't want to have too many variables, so I'm going to use y minus x. And there's my equation right here. All I have to do now is take the derivative. I wouldn't take the derivative here, though. Very complex. So what I'm going to do instead is cross multiply. 16y minus 16x equals 6y. Solving for y, I'm going to get 10y equals 16x. So y equals 16 over 10x. So I can get my equation there. And now I can take that function's derivative. This is much easier to take the derivative than this one. So we get dy dx equals, be careful, 16 over 10, whoops, sorry, that's dy dt, 16 over 10 dx dt. And then to find dy dt, I could just plug it in. Dy dt equals 16 over 10. And what did we say dx dt was? -5. So I just multiply this by -5. And what we wind up with, very quick and easy, we wind up with a -8 feet per second. So what that's telling me is that the tip of a shadow is heading towards the light at a rate of 8 feet per second. So I'm going to write that over here. I ran out of room, so I'm going to go ahead and write that up here, okay? The tip of the shadow is moving towards the light at a rate of 8 feet per second. And that's what we're going to say there. Now, part B, very easy. It says at what rate is the length of a shadow growing when it's 10 feet from the light. Now, also notice up here, did we use the 10 feet at all? No, it just goes away. So what that tells us is that his shadow moves at the same rate no matter how far away Gandalf is from the light. So for part B, it says at what rate is the length of a shadow growing when he is 10 feet from the base of the light. So that's very easy right there, okay? Remember how we wrote down the length of the shadow was y minus x? Well, we want to find dl dt. So I just take the derivative. dl dt equals dy dt minus dx dt. So dl dt, dy dt, which we just found is -8, minus dx dt, which we said was -2, and we get, whoops, sorry, it was -5, sorry. And what we wind up with is -3 feet per second. So what's that telling us about the shadow? Yeah, that the length of the shadow is decreasing at a rate of 3 feet per second. And there's our answer. Very easy to do. Alright, last one. Okay. You want to know the shadow problem. One, I like it. You're going to see it again. I promise you that. Okay? Alright, C. This is kind of a cool one right here. Han was pulled over for speeding in the Millennium Falcon. His the patrol spaceship's car was parked 60 feet from a long cliff face. Han noticed that the light on the top of the patrol ship rotated at a rate of 60 revolutions per minute. Being bored, Han decided to figure out how fast that beam of light from the patrol ship was moved along the cliff when it made an angle of 30 degrees, with the line perpendicular from the light of the cliff. So I'm going to draw this out. First, I'm going to draw a long, long cliff. Here's my cliff, okay? And here's the patrol car. Now, we're told that the patrol car was parked 60 feet from the cliff face. Okay? And then, what we want to do is we want to find out how fast that beam of light is traveling when this angle is 30 degrees. So what I'm going to do is I'm going to label this. Again, we're going to do a right triangle. We'll call this A, B, and C. Now, we're in calculus, so we're going to call this radians, so pi over 6 radians. So let's find out what we're trying to find first, okay? We want to, what are we given? Not much yet, but let's take a look here. We're asked to find the following. How fast that beam of light moves along the cliff face when the angle is 30 degrees. So we're asked to find dB dt. So what I need to do is I have to solve for dB dt. So I need an equation, okay? We're looking for that rate of change right there. How fast that beam of light is moving along the path there. So remember, because here's the light, it travels like this, right? Now, so to figure this out, we have to use a trig function. I'll tell you why. Because of an angle, we have a theta, which means we have to use a trig function. So the question is, which one do we use? And you might recall my hint from earlier. Look for the one that's constant. A is constant, so I need B and I need A. So I'm going to use tangent. So A is constant. And I need the opposite side. So what am I going to use? Tangent. Tangent of the angle is equal to B over A. But because A is a constant, I can write this as tangent of theta equals B over 60. Once I get here, I'm going to take my derivative. I get secant squared theta d theta dt equals, and again, I can just write this as 1 over 60 times b. Makes the derivative much easier. 1 over 60 db dt. So there's my derivative. So I need to take a look at everything I need. Okay? So if I look over here, what do I need? I need the secant of theta. I need d theta dt. So I'm going to write these out. These are what I need. If I can solve for secant of theta and d theta dt, I can get db dt. I can get the rate of change, how fast it's moving. So secant of theta, very easy. It's just the c over my adjacent. So it's going to be something over 60. So I got to be able to get c there, right? So, or since I already know the angle, it's really the secant of pi over 6, right? Which is 1 over, that's the cosine, which is root 3 over 2. So I get 2 over root 3. So I can write this already as 2 over root 3 squared equal to 1 over 16 dB dt. Now, to get dB dt, I got to think, what unit will that be in? That should be measured in radians per minute. I know that because we measure angle in radians. Radians per minute. That's what I'm looking for. So here's what they tell me. It's rotating at 60 revolutions per minute. Well, that means, remember, 1 revolution is 2 pi radians. To get 60 revolutions, we're going to take that 60 and multiply it by 2 pi. So we know it's 60 revolutions per minute. So therefore, we're going to take that 60 multiplied by 2 pi, and we get 120 pi radians per minute. And there's our unit. So I'm going to multiply this by 120 pi. I'll split that up there. So solving for dB dt, we're going to get, this becomes 4/3 times 120 pi times 16. Where did I get 16 from? Oh man, that's terrible. That should be a 60. 60. 60. There we go. So multiplying it by 60. I made it, be careful, that was 1 over 60. I put 1 over 16. So most of you guys probably already caught that and are laughing at me right now. That's okay. And that's going to be dB dt. And if I simplify that, that's 960 pi, and the units are feet per minute. Now, if you really want to know, in the real world, that's 3,015 feet per minute. All right, so that's the end of part 2. It was a little bit longer. Again, please make sure you fix that 16 to a 60. Okay, I'm getting closer to 60 than I was 16, so maybe I was just thinking, man, I wish I was young again. All right, so there you go. I'll see you guys tomorrow. Bye.